How's everybody doing? Good? I want to key off some of the things that Rafael talked about. We're going to take a bit of a deeper dive into design. And one thing he said that really resonated with me, and it's core to a lot of our thinking inside research, is that we are at an incredibly pivotal moment in time right now. And we are very close. I think all of us in this audience are close to the world of physicality, of this world of design. And while we're living in the ChatGPT area right now, we're feeling the digital world change, the physical world around us is about to start changing. And this is when we're really, really going to appreciate what AI is going to bring to the future. So I want to take you on a little bit of a journey today. We're going to dive into what we do in Autodesk Research. So I'm the Senior Vice President of Autodesk Research, which is another way of saying that I'm the person that gets to have a lot of fun at Autodesk, while my colleagues like Jörg do the real work. So I hope you enjoy the fun that we have, but it's serious fun. It's fun that helps us understand the future. So let's talk a little bit about Autodesk Research. So Autodesk Research is an organization. It's around about 250 people. We have labs around the world. And our job is to stay 10 years ahead of the industry, 10 years ahead of the company. We have experts in technologies. We also have experts in industries, and we bring these experts together to effectively de-risk the future. We want to try and understand what really works. You know, in this day and age, there's a lot of hearsay, there's a lot of speculation, there's a lot of hype. It takes real research and real experimentation to actually figure out what's truly going to matter to us. So that's at the core of what we do inside Autodesk Research. Now, one of the labs we created inside Autodesk Research some years ago was our AI lab back in 2018. And we created this when we noticed the speed of AI beginning to evolve, and we were working with all folks like you. We were looking at the kind of problems you deal with. We'd already been working on things like generative design, using computational techniques. But we're like, hang on, this AI stuff's going to fundamentally revolutionize how people understand design problems, the kinds of things they can solve, and even more importantly, I believe, is how you interact with technology. Because I think through most of human existence, we've kind of dumbed ourselves down when we use technology. Why do we have to use a keyboard? If you think about it, a keyboard is a really stupid thing. It's a whole bunch of the letters of the alphabet, and you press buttons. We're going to look back on a keyboard and laugh in the future. It's like, really? That's how you can just talk to your computer? Has anybody here seen that old Star Trek episode where I think they ended up back on Earth, and Scotty's he picks up the mouse and he goes, hello, computer? Computer? And it's like, no, you got to use the keyboard. What the hell's a keyboard, right? That is how we're going to look at the world that has gone by us. So there is some incredible advancements we're going to take a look at in AI that we've been toying with, trying to figure out how they're going to impact design. Also, our AI lab has been working in the field of geometry. So we do an enormous amount of work in structure and how to build things. But what we also do is we couple it with another part of our research group, which is our technology center. So we have 4 technology centers around the world. So what's a technology center? For those of you who maybe have visited our technology center, you will have seen that they're full of machines that make things. They have additive machines, subtractive machines, measuring machines. We have motion capture stages. These are places, again, like I said, where we're making things. We're actually doing and we're creating and we're working with, sometimes it's our customers, sometimes it's startups that come and do a residency with us. Sometimes it's an academic researcher that comes and works with us. But they're always making something. And another thing that Rafael said earlier on towards the end of his talk, something about the physicality of things. How when something becomes physical, this is when people's brains light up. They actually understand the problem. And this is what happens in these technology centers. When you're using these digital technologies, but you're actually making a physical artifact. So you understand the problem at a much, much deeper level. So here's some examples of things we've created over the years, starting from a lunar lander that we partnered with NASA JPL on. It's a lunar lander for the moon of Jupiter. Uses a new computational technique, hollow topology optimization combined with traditional forging to make this amazing lander. We were able to work with General Electric to take a manifold of a jet engine, which is typically over hundreds and hundreds of parts, consolidate it down to one part, and do, I think there was a 30% drop in 30% pressure drop improvement inside the manifold. This was, again, something that had never really been done before. It required all these digital tools to come together in the space. We've 3D printed a bioplastic bridge with embedded sensors with one of our structural engineering customers. And we worked with a company in London developing a new catalytic converter that can take a composite liquid form of hydrogen that is actually completely inert and safe, and it'll convert it dynamically into actual hydrogen gas, which can then be ignited and used as a fuel right at the point of usage. All of these things, as you can tell, are real-world practical things, but they required a new approach to being designed and created. It required new techniques to understand things. This is really, really what we try to do in these centers, and it allows us to bring together all of our research and figure out what's really going to have an impact. So today, what I really want to do is I'm going to use a triptych here. I'm going to use a structure of 3 to really look at how this world of design to make is changing. And we're going to start with shaping, how we create form, because at the core of all physical design is creating a shape or a form or a structure. Then we're going to move on to how does that perform. It has to live in the real world. It has physics, it has behavior, it is around things that move and do functional things in the world. And lastly, we have to actually make the thing. So AI is impacting every one of these stages. It's impacting more than these stages as well, but these are the 3 that I think are most relevant to look at right now to truly understand what's coming. So let's start with shape. And if you go down to the exhibition floor, you'll see our Blank AI tool. So Blank AI is a new tool from us. You can use a prompt to very, very quickly create a basic car shape, sort of at the conceptual phase. You can take that basic car shape, you can import it into a tool and start preparing it for presentation, give it color, give it texture, give it context, and then you can go even one step further. You can take that entire shape and move it into our alias software and turn it into sub-D surfaces and use it as a starting point for an actual design. So I find this interesting because this solves a problem that's been bugging me in design tools for years, and I call it the blank canvas problem. The problem that when you load up one of our design tools, what do you see? Blank canvas. And there is nothing worse for creativity than seeing a blank canvas. You need something. You need something to inspire you. So now you come into Blank and you just type a prompt, and instantly you've got something. You don't just have one thing, you have many things. And you can start ideating and iterating. That's the kind of thinking that an AI can enable in a designer, which is what really excites me about what we're doing here. Now, I want to jump, so that's in the product. I want to jump back into Autodesk Research. So something we launched last year was Project Bernini. So Project Bernini has come out of our geometry lab, and this was based on the world's largest data set of 3D models. We collected this massive, massive data set, and we also invented a new kind of foundation model. It's a foundation model that directly produces 3D. It reasons in 3D. It doesn't think of 3D as a picture or a surface or anything like that. It thinks of it volumetrically. It actually understands that it's 3D inside and outside. It uses a special wavelet compression technique to compress the data and the reasoning inside the neural network. Now, let me show you a little bit about what Bernini does. I'll show you a little demo here. But what's neat about Bernini, the real reason I'm showing this to you, is it's showing you some of the new interaction models that we're going to be seeing in the future. So Bernini, you can use text prompts, you can bring an image, you can bring a point cloud, or you can even sketch. And not only that, but you can do them all at the same time as well. So you can say, I want a chair, but I'm actually going to draw you the kind of chair that I want. But given that this is an automotive conference, we're going to draw a car today. So you're going to see me with my Apple Pencil, just very quickly. Imagine this is the very beginning of an exploration, and I just simply want a shape. So I break out my pencil, and I start to sketch. All right, this is me sketching out a new car shape. Now, I'll tell you, if any of you want to talk to me later, I'm happy to help you do car designs. You'll notice I'm a fantastic car designer. Pretty amazing car. But let's see how quickly this turns it into 3D. Bam, there we go. Got a 3D shape already. you'll notice it's actually hollow inside, and it's giving us 4 options. This one is understood that cars are sort of a hollow body. The next shape, you'll notice it's added mirrors to the side of it, and it's actually found all the wheel wells. So you can see what this model is. I didn't tell it what a wheel well was, right? But it understood that. This is what's interesting about a volumetric model, is it actually understands the 3D structure. It understood that the inside of a car shell is hollow. It understood what a wheel well was. It understood the placement of mirrors. This is kind of fun. It sounds kind of basic, but it's kind of fundamental that it actually understands structure. And if I can create shapes that easy, I mean, how many seconds was that to create it? You can imagine where design is going in the future. This is all based on research that is, like I said, has come out of our core geometry work. And like I mentioned earlier, our lab is the world's leading publisher now in this space. We're looking at ways that AIs can reason about how components come together in complex assemblies, how shapes are formed. But the one interesting thing that is consistent throughout all of these papers is that we are looking for precision and controllability. There's a lot of things that are happening in AI today that are just sort of fire a prompt out, get something. You can kind of control it, but if we really want design to work well, designers have to feel comfortable that they still have control. There's a sort of an oscillation that goes between the AI producing something, inspiring the designer, and then the designer taking control and doing something, and then the cycle kind of repeats. We really want to enable that kind of cycle. So that's the sort of common theme in all these research papers. But now I'm going to show you something about the real future. So if you've all seen diffusion models, stable diffusion, mid-journey, what they do is they basically they create images right from noise, and they iterate it and produce hyper-realistic imagery. What you've just seen is diffusion applied to actual accurate 3-dimensional geometry. So we have this working now in our lab. We can take a whole random cloud of faces and edges and actually diffuse it and control it with precision into actual geometry. So stay tuned on this. You're going to hear a lot more from us about this technology and where it's going. So with that, I'm going to wrap up the shape side of things, and we're going to just make the observation that everything I've shown you up until now is static, right? It's a chair, it's an object, it's a thing. It's not living yet. And everything in the real world makes a noise when I hit it. It has function, right? So how do we bring function to something? And we get to performance. So again, I'm going to start with something that's in our products today. It's something new. It's an acquisition we did last year called Navasto. And Navasto allows you to start directly with inside Alias and take your model and apply simulation directly to it. It's rapid AI-based simulation. In this case, it's showing you where the incident forces on the car of air forces on a car. But what it does is being able to give you this kind of information very, very early and instantly. It's not exactly precise. It's pretty precise, but it's enough to give you as a designer this very quick feedback on what is working, what is not working in your design. Instead, as most of you know here who are in automotive design, simulation was something we did at specific intervals through design historically. We checked our designs. That's what simulation is for. We're inverting that world now. Simulation is the thing that brings life to your design. As you're working, it's constantly giving you feedback. It's telling you how your design is going to perform. It's giving you information that you're going to need at best early on in your thinking. Right? So this is something I want you to take away. This is where simulation and the sort of liveness of design is going. But this requires real-time simulation. And the only way to achieve real-time simulation is through advances in computation and AI. So let's take a look at what some of this looks like inside Autodesk Research. So this is some of our real-time AI working here. And on the left, you're seeing real-time contact physics. This is Newtonian contact physics happening. We've got a robotic gripper. The robotic gripper is going to come back later, so just stay tuned on that one for a while. That's a common thing we use as a sort of a sample problem in our research work. And then you're looking at this sort of screw thread, just sort of just assembling itself over there, purely completely 100% real-time simulated with AI. And then on the right, you're seeing fluid dynamics sort of simulations, again, all real-time. So these engines were it was not possible to build these engines even just a year ago. Within the last year, they've become feasible, and they're becoming more and more accurate. They're becoming faster. They're becoming lighter weight all the time. So I find this really, really exciting. The core technology is now there to start bringing this real-time simulation to life. So let's take a look at what you can do if you have real-time simulation, because it's not just about doing simulation. It actually changes the way you do design. So let's go to creation of gear trains. You want to establish a set of gears, right? And you're going to take a rotational force that's at one point in space, and you're going to translate that torque to another point in space. Maybe it's a linear force over here or another rotational force. And you want to figure out what are the gears between those. The system you're seeing play here is actually an AI-based system that is using real-time simulation to understand how the gears are coming together and instantly solving the gearing problem for you. It's showing you hundreds of possible solutions to your gear train. It even calculates the bill of materials, and as you can see here, allows you to sort by the cost, so you can immediately find the cheapest set of gears. Now, again, any of you that are working on gear trains know that sometimes gear trains take a while to work through, but they're not you wouldn't consider that as a super creative part of the design work. That's something that you just kind of have to do to make a part of an engine work, right? Here's a system, again, with real-time simulation and AI, can instantly produce a set of results as part of your design work. An alternative user interface here is, instead of having it automatically produce it, what if you start designing your gear train? You know, it says, hey, here's the first component you might want. You select the first component, you put it in, and immediately the catalog updates to show you your next option of components. So you still have it. Remember I talked about control, how a designer actually still needs to have control. Here's somewhere where the designer has control, but the AI is kind of overseeing what they're doing. It's constantly giving them this custom catalog that's being computed, again, using the AI and the real-time simulation. Now, the next thing I want to talk about is accuracy in simulation. So, as most of you probably know already, any computational simulation is never 100% accurate. It's the sort of mechanical implementation of a set of equations inside of a computer, right? It's never going to fully represent all of the complexities that happen in the real world. So we decided to start tackling this problem inside Autodesk Research. We started this about 3 years ago. We decided to take, in this case, a heavy lift drone, one of those very, very large drones that this drone carries about a 200 kilogram payload. And we decided to figure out what is truly going on in that drone when it's really flying. What's actually happening? Because the company that had built this drone, they were fairly new at designing drones. They'd run some very basic simulations, but most of the aeronautics and all the performance characteristics of this drone were based on engineering rules of thumb, things that people just kind of knew that they believed would work. We were like, well, I wonder if this is true. So what we did is we took the drone, we ran all the simulations, the traditional simulations, and then we flew the drone, and we compared the performance of that drone in reality to the performance in the simulator. Now, on the drone, we placed accelerometers, we placed force sensors, we can measure the airspeed around it, rotor speed, all the torques on the frame of the drone, a whole range of things. So we really had this quite high fidelity sort of telemetry of what was going on inside the drone. So we could compare these things quite accurately. Now, taking that difference allowed us to start training. So remember, we've just talked about how AI is the mechanism by which we can create real-time simulation. Now, the reality of AI is AI gets trained on data, right? So typically, real-time simulation AIs are a combination of bringing the equations of simulation together with an AI and then providing a whole bunch of data. Often it's synthetically generated data to train these AIs on how to simulate a very specific thing. So what if you could bring this real-world data in as well? What if every time you made a product and that product went out to the world, what if every time you sent a new car out into the road, it fully measured itself and sent all that data back, and all that data went into an AI system that suddenly just got better and better and better every time at understanding what's actually happening in the real world? So the last video I'm going to show you here is actually that drone now. We've captured all of that information. We've trained an AI model on how that drone actually performs. And now we're in the design tool, and we're actually watching the flight path. We're watching the performance of the drone. We're watching those white arrows reflect the lift forces that the rotors are producing. You can see various graphs of thrust and everything that's happening at the same time. But what's interesting here is we're in the actual design tool. So while we're watching this, the AI is actually placing the forces on the actual 3D model in the tool. Now I can go back into the design tool and start looking at my 3D model. I can understand those actual forces, and I can actually start using optimization techniques to say, take part of this drone now and optimize a part of it. Like, understand, could this one beam within the drone be thicker, for example, to stand the loads that are being placed on it in actual real life, which wasn't, by the way, predicted with some of the original simulations. So if you think about this, this is really exciting. I mean, we have this future where understanding how things perform in reality is getting faster and faster. It's becoming real time, so we have it there all the time. But it's also getting better because it's data-centric. You can actually take things that are happening in the actual world and constantly improve those simulations. All right, so we've looked at design, we've looked at shaping things, and we've looked at how things perform. What's left now is how are they made? So as we go into how things are made, we're going to take a very specific lens. Obviously, in our technology centers, we've got additive techniques, we've got subtractive techniques, we've got human beings making things, we've got all of that. But we also have a robotics lab. And our robotics lab, we established our robotics lab back in 2015. And the fundamental premise in our robotics lab was that we could take the information that is embedded in CAD files, purely the information embedded in CAD files, and train AIs to closed-loop control robots to assemble things based on that data. We started with small things. We started with Lego. You see on the top right there, that was an automatic Lego building robot that we built some years back. And then at the bottom right there was something we called the Arroyo Bridge, which was a bridge somebody commissioned in the south of California. It was a beautifully designed bridge, but it has this kind of awkwardness to it that every piece of framing in that bridge is at a different angle. There is no uniformity, there's no symmetry to that bridge. So it's incredibly difficult to actually weld and create that bridge. So again, we created a robotic system that was able to bring these bridge pieces together and weld them into the shapes that they are. So it was basically a robotically built bridge. So small-scale Lego, large-scale bridge. But the common thing in both of these is that we were using the CAD data to actually let these robots learn in simulation. And the idea is, now imagine this, you're a designer, you've designed a new component, it's 5 o'clock in the afternoon, you've finished designing your component, you save it off, you check it into the software, you go home. And while you're at home, the AI is taking all the components designed today, they're putting them into a simulator, and they're starting to imagine robots grasping those components. They're imagining robots assembling those components. And they're doing this hundreds of millions of times over, generating these massive data sets that update the AIs. And the next morning, when you come back to work and you switch on your robots, they can recognize the component you designed the day before, and they can start to work with it and assemble it because they actually understand it physically. So that is what we're after. To get there, one of the first things we did is we designed this thing called ABC Grasp. So you have to grasp something. You have to be able to hold something. That is your fundamental starting point for any robotic problem. So what we did is we built this massive data set, and we've trained thousands and thousands of digital robots to spend a whole bunch of time figuring out how to grasp objects. And it's learned a foundation model that is actually a kind of a grasping foundation model, if you want. Every time it sees something, even an object that it's never seen before, it has an intuition now of how to pick something up and hold it, especially for the job of actually doing something with it, like inserting it some way. So that's the first part, is grasping. The next part, and this is very obvious to most human beings, but generally not to robots, is the sense of touch. Right? So the next part is about learning insertion policies. When you're inserting something, when you take that little USB-C cable or your lightning cable for your phone and you insert it, you don't look at the edge of your phone, probably most of you, I would imagine. You sit there and you jab it in, you can kind of feel when it clicks in. You're using your sense of touch. So we want to give robots the sense of touch in order to do insertion. Insertion in manufacturing, as probably many of you know, needs to be incredibly precise. This is actually a precision that is generally far beyond what cameras themselves can actually see. So the robots you're seeing here are using torque sensors inside them. There are AIs that are learning purely torque-based feedback. So it's purely feeling its way in. That gear that it's placing, I think it's probably placed it already, that gear that it just placed over here, the tolerances on that gear were about 1/10 of a millimeter. So, the only way you can make that work is really sort of feeling your way through. So this is if we can solve the vision problem of how to grasp something from seeing it, and the insertion problem of using sort of force feedback, plus all this learning from CAD data, we believe that brings us a lot closer to actually being able to automate this. Something else we've been working on, this is a really fun project, this has been with MIT, is how to build something. Like, if you have a whole range of things, how can you actually build this in the real world? And I love this little truss table thing over here. It's not obvious, actually, how to assemble this, because, if you hold it that way, it kind of falls apart. You've got multiple pieces, so which ones do you put in first? There's only one really correct way, and you've actually got to put it, like you can see, it's easy for a human, right? You can kind of feel your way, click it in, but it's not intuitive for a machine. So what we did is we trained, again, we built a whole bunch of data, and what we did is we disassembled things. We digitally disassembled things, because if you think about it, disassembly is the reverse of assembly. So what we did is we taught AIs basically how to disassemble stuff and then reversed it. And if you reverse it, but you also introduce physics into it, so that it understands that not everything kind of floats in the air. Things are going to fall off if they're not the right way. It actually ultimately learns how to assemble things. So now we can take that assembly that you check in the night before, and again, put that into the AI, and it can actually understand what are the sequences of operations that the robots have to go through in order to assemble this. All right, so the last video I'm going to show you is actually what we consider one of our challenges. So this is the challenge from last year. This is the 2024 challenge. The 2024 challenge was to assemble the truck of a skateboard. So the truck of a skateboard is the part with the wheels on and the axle underneath. It's generally about 7 to 9 components, but they're tricky components. They come in at a very weird angle. There's strange fasteners. You have to do things with multiple grippers at the same time. So that was one of our first challenges last year, what we wanted to do is save those components in, come back the next morning, like I said, and have the work cell be able to design the truck. So it starts off, this is what the truck looks like. This is the digital CAD representation of it. And this is our digital simulation of it. So the digital simulation is of the work cell. It can fully simulate everything from the forces to the vision, what the cameras are going to see, what the components are going to look like. And now we go to the actual work cell. So you'll notice the work cell here has a set of tools along the one side. These are interchangeable end effectors. Some of them have got ratchet screwdrivers. Some of them have got different grippers. So there's 2 arms working in tandem with each other. They can switch out tools as they go. Now, what I'll tell you, the only thing pre-programmed here was telling it what sequence we want it to do the operation in. So go and grab this thing, go and build this thing, go and build that thing. That's it. There was no other programming here. So the traditional robot programming of move the arm over here, grab the thing out of that bin is not here at all. It's literally go and take that kind of nut, put it on the screw, turn it this way, do it that kind of thing. That was the only programming that was involved here. You can see what it's doing is it's doing some very, very, very intimate pushing and nudging of bolts into holes, carefully inserting. It's using both the vision systems and the sort of force feedback systems to carefully bring these things in. There you see it's used the ratchet ratchet driver now to finally fasten the last part of the truck together. So this just gives you an idea now, I want to leave you with, is this is the future of how things are going to get made. The idea that you can sit there, you can design something during the day, AI can guide you through what you are doing, and at night the robots will learn how to actually work with it. And you can immediately start cycling, you can try things out the next day if you see some problem with what the robot's done. That data has probably been collected and put back into a digital twin that's now back available in your design software. So this entire cycle of design and creation is speeding up and getting created in a way that we've just never seen before. Anyway, I hope this has inspired you. I hope it's given you some sense of what the future of designing and making truly looks like. And again, I'll come back to what I said in the beginning. We live in an incredible time right now. The chances of making things in a better way around the world, cheaper, affecting our environment less, it's ours for the taking right now. I'm very, very excited about the future, and I hope you are too. Thank you very much.